Anyone have any questions before we get started?
Hello.
Yeah, Andrea, how you doing?
Hi, I'm good. Thank you. I had a quick question about the online test that was due last night.
Okay, yes.
I I was wondering if you could maybe open it again by any chance.
You goober. Yeah, I will.
Thank you so much. I really appreciate it.
No
Thank
problem.
you.
All right, I'll leave it open for another day, so that's for everybody. Also, wanting to mention this is for NO2B, of course, but I'm making a mention that's also for O01B. Or actually, more specifically, that is for O01B, not N02B. One of the students in the class, Jeremiah, found some problem with pendulum in one of the labs. I thought it was last lab, so I went to check it real quick. Actually, I looked at it one time when he first mentioned it to me. I thought I'd found some fix for it, but then I completely forgot about it, and it's been a week now, so I completely forgot. So he had some problem with that lab, so I need to find out what lab that was because I just went back and tried to look for it. And when I do find it, I'm going to delay the deadline. I assume if he's having a problem, everybody is. But if anybody's not having a problem and was able to do all the labs, then by all means, let me know so I can let him know and find out what's going on. But I've got to do some research on that just to figure it out. I'm pretty confident it wasn't last week's lab because last week's lab was projectile motion, and this one had a period of the pendulum problem. So I think it was linear graphing too. Y'all might even remember that. Y'all had the same lab more than likely, but maybe not the same week as the O01B. So, anyways, that's just for everybody in O01B. I'm going to delay that. So, even if I don't change the due date, I'm definitely going to give you an extension on that just because Jeremiah told me he's having some difficulties with it, and I did not get back in time with him to correct that. Uh, we do have a test this week. Remember, you have until the 21st to complete your online test. That has to be proctored. I will be sending the email to Mr. Dr. Johnson, or yeah, I think that's his name, Dr. Johnson, so that he'll have the password. When's y'all's lab? Is that Tuesday or Thursday for NO2B? Anyone?
Yeah, we have labs on Tuesdays and Thursdays, so he's gonna let us do it this upcoming Thursday.
Okay, Thursday, cool. All right, I just
Yeah.
want to make sure. I was pretty sure he wasn't doing it Tuesday, but I'll make sure I send him the stuff before Thursday. Thanks for that, Darius, too. Uh, all right, well, let's go ahead and get started. Last time we completed chapter 9, which was on conservation of momentum. I just looked and I've got to clean up the homework for chapter 10. I think chapter nine's been corrected, so that's good to go and everything's working and has been for some time. But chapter 10, which we're just starting tonight, that's going to take a little bit of work, but it should be fixed right after class. So I did open the module. It's week 9 module, July 14th to July 20th. That's up there. I've got videos for chapter 10. I've also included some more videos that are important and helpful for chapter 9 in the previous week's module. So y'all might want to check that out as well. There's a couple of really cool problems where you basically have, imagine a train car sitting on a train track and on the train car is mounted a cannon inside the train car, and inside the train car is like let's say 20 cannonballs. And what you're going to imagine is taking the cannonballs, which are all stacked against the end of the end of the train car, and then, of course, just slightly farther from the end of the train car is the cannon, and we have the total mass, that sort of thing. You're going to take one by one, put the cannon in the cannonball, or put the cannonball in the cannon, fire it, and of course, immediately upon firing it, the whole cannon or the whole train car is going to move backwards while the cannon fires that way. And then when the cannonball hits the other side of the train car, that's going to bring the train car to a stop. And we're going to go on the assumption that cannonball will then fall straight down and land right there on that other end. So we're actually, in addition to firing the cannons and all that stuff, we're moving all the 20 or so cannonballs from, let's say, the west end of the uh, train car to the east end of the train car. And what they ask is basically how far has the train moved once, X number of cannonballs have been fired. And you can do that with conservation of momentum, and it's really neat and that sort of thing. But the other thing is you can completely do it with the idea that the center of mass doesn't change if the net external force is zero. So there's two really good ways to do it, and you get the same answer in both cases. I did that, worked that out for you some time ago. It's on my YouTube channel, and I put the links to that on the week 8 module. So definitely check that out. I've got to move that over to the O01B class as well for their week 8. But anyways, that's where that is. Uh, Anybody have any questions before I get into chapter 10, rotational motion? Okay. Well, I have my iPad fired up and I'm getting ready to start taking notes and sharing that with you, but I wanted to discuss the rotational motion chapter, which is what chapter 10 is called. Chapter 10 is called rotational motion, and it has a nice little picture of a merry, well, not really a merry-go-round. This is amusement park ride. Dang it, Ferris wheel. There's a Ferris wheel in the distance. There's also one that's rotating sideways, and that's the one whose name I can't think of right now. I'm drawing a blank. But anyways, carousel. I think the carousel is what that's called. Anyways, the sections of this chapter are 10.1, angular quantities, and the majority of what you have to understand for chapter 10 requires your knowledge of the S equals R times theta equation that you learned in trig. So remember, S, a little arc length on a circle of radius R, is the length that's traversed if you allow the radius R to go through an angle theta. And then that gives you S, the arc length is R times theta, where theta has to be measured in radians. That equation is fundamental to all of this chapter. So that's probably the single most important fact that you need to go into this chapter. And from there, we can discuss things like obviously distance traveled, which was in linear motion a quantity x and was normally measured in meters or miles or light years or whatever. And now in angular quantities, we're going to slip and into a different mindset and imagine it as you're going to rotate through some angle or you're going to move through some angle in circular sort of motion. And instead of having x represent the distance traveled, you're going to have theta represent the angle traversed. Uh, you will still have a velocity. You'll have a tangential velocity, and that tangential velocity, if you use S equals R times theta, you can take the derivative of both sides. That'll give you ds over dt is equal to r d theta over dt. And ds over dt, you might notice, obviously has units of meters per second, and lo and behold, that is the tangential velocity. The r being a constant allowed me to skip the derivative of it, and I just took the derivative of theta with respect to time. And that d theta over dt looks just like a velocity formula, but now it comes out in like radians per second. And by the way, all the equations work if you use radians for the angle. But you can also use other things and other quantities. But if you're ever in doubt, just use radians. Now, the other thing is that d theta dt is a quantity that we call the angular velocity or the angular frequency, and it's given the symbol omega. And then similarly, if you take the derivative of v equals r omega, which is what I just sort of derived for you in your head or in my head and explained it to you, if you take the derivative of that equation, then you get dv dt, which is obviously an acceleration. In this case, it means an tangential acceleration. And we get dv dt equals r times d omega dt, and d omega dt is what we'd call alpha, and alpha is what we'd call the angular acceleration, and that'd be measured like in radians per second every second, whereas the omega was measured like in radians per second. So those are some of the angular quantities we'll be dealing with. We're going to have analogs to all the stuff we learned in Newton's laws as well as kinematics, and I'll go through that with writing it, not just not just saying it in words. Section 10.2 is the vector nature of angular quantities. It turns out that uh, there's these things that are more what we call pseudo vectors. And for instance, the cross product, anytime you use a cross product to calculate a vector, it is essentially going to turn into a pseudo vector and doesn't transform the same way. And that's what happens with treating the angular uh, displacement, which is theta, or the angular velocity, which is omega, or the angular acceleration, which is alpha. That becomes a problem as well because we're going to use sort of a right hand rule. And what will turn out is that theta and that omega and that alpha are not truly vector quantities. So that's what 10.2 is about. 10.3, just like we did in chapter 2, we're going to start off with a constant acceleration. Only 10.3 is constant angular acceleration, alpha, in other words. 10.4 is when we introduce torque, and torque is the rotational analog to force. And 10.5 is rotational dynamics. So that's where we're using sort of the equivalent of Newton's laws of motion, but in this case for rotational motion. 10.6 is problem solving and rotational dynamics. 10.7 is determining the moment of inertia. So we'll learn another calculus related formula for calculating moment of inertia. A little more complicated, but also a little less complicated. Whereas, for instance, when you calculated the center of mass in chapter 9, you had to do an integral of x dm and then divide that by the integral of dm. In this case, it's just going to be the integral of r squared dm, where r is the distance from the rotation axis to the differential mass element dm. So I, the moment of inertia, will be the integral of r squared dm. That's what we're going to learn in a moment of inertia. We're also going to branch out and jump as far away as going into kinetic, or excuse me, into conservation of energy again. So we're more or less fitting chapter 2, chapter 3, chapter 4, and chapter 5 all in one chapter with regards to angular motion, specifically because we're talking about kinematics, talking about dynamics, which is when F equals ma comes into play, and then the alternative to Newton's laws, which is conservation of energy. So you can see that's actually covered in 10.8, where we talk about rotational kinetic energy, and then 10.9, where we talk about rotational plus translational motion. And then 10.10 gives you a nice description of why does a rolling sphere slow down. So it's a really good explanation of how the friction works for a rolling object. So we've already learned about static friction and kinetic friction. There turns out there's going to be a friction as well associated with things rolling along a surface, which is what we're talking about in this angular motion stuff. But in order to understand it, you should read over that section 10.10. It is an asterisk on that section 10.10, but I highly, highly, highly recommend you read it. I may ask conceptual type questions from that section uh, on your tests and final exams and that sort of stuff, but that's pretty much all I would do. All right, now that I've gone over that, let's go ahead and get started. So I'm going to turn on my iPad and share the screen with you in principle. So let me go ahead and share screen. Feel free to ask me questions at any point, as well as right now. Okay, so we're looking at my iPad, and I want to start off with the equation that we were just talking about. I'm going to do so first by drawing a circle. Okay, there is a circle. We're going to say this circle has a radius r. And what we're going to imagine is we allow that angle, that radial line to move through an angle theta. And then we wish to measure this bit of arc length. In other words, along the curve, not a straight line, which would be called a chord, but along the curve is the quantity s. And we know, hopefully, from trigonometry that s is equal to r times theta, and that theta has to be in radians. And in some sense, you can sort of think of this as the definition of radians. And for instance, if you imagined uh, the radial line r being swept not just through theta, but through the whole 360 degrees, what you would get is the arc length around the whole circle. There's a special name for that. It's a C word, even though it doesn't sound like a C word necessarily. Anybody recall what that C word for the arc length around completely around the circle is? Anyone? Anyone? So it's the C word called circumference. So the reason why I'm bringing that up is because we know the formula for circumference. Circumference is equal to 2 times pi times r. And if you combine that with s is equal to r times theta, what you see is 360 degrees must be equal to 2 pi radians. And that is a conversion factor. Another conversion factor, of course, would be you can write it as 360 divided by 2 pi, but you could also write it as 180 degrees divided by pi. And then, of course, you can also write these in the other direction. You could put, for instance, 2 pi over 360 degrees, or you could put pi over 180 degrees. And you could say, for instance, if I take pi and divide it by 180, 3, 3.14159 divided by 180 gives me, oops, I want to do that the other way. I'll just flip it over. So I'm going to take that, raise it to the negative 1 power. Oops, clearly cannot do that. Let's say shift answer, and I'm going to raise that to the negative 1 power. And what you'll see is that's 57.29. And actually, I should probably put it the other way. I won't put it right here. I'm going to say equals 57.296 degrees per radian. So you now know that a radian is actually a quite big angle. It's even bigger than 45 degrees. It's roughly 57.296 degrees. Now, the beauty in this is, yes, this formula always works. It always gives you the arc length, and as you can tell, it even gives you the idea of the arc length becoming the circumference if you make a complete rotation of the radial line all the way around the entire circle. And that, of course, allowed us to conclude that 360 degrees is equal to 2 pi radians. But in addition to that, we can take derivatives of it and come up with meaningful stuff. So I'm going to go ahead and circle this just to, or box it off just to remind you that it is important. And I also want to remind you that theta has to be in radians, so I'll box that off. Now, the other thing I want to do is I want to take d by dt of s equals r times theta. So what that means is I'm going to take ds over dt on the left-hand side, and I'm going to take d by dt of r theta on the right hand side. But if I go on the assumption that r equals a constant, then I get ds dt is equal to r d theta dt. Now, if you look at the units of this, you'd see that ds dt has units of meters per second, for instance. And in fact, it is a velocity. So we're going to say v tangent is equal to ds dt. Now, what do I mean by tangent? I mean, if you're traveling around in a circular path, okay, then at each point, your velocity is parallel to a tangent line right at your location. So if you made a tangent line at the location on the circle that you're at, then your velocity vector would be parallel to that, and that velocity vector represents your what we call your tangent velocity. Your tangent tangential velocity. However, you could also have a velocity perpendicular to that that would point radially inwards, for instance, and that would be considered your centripetal or your radial velocity or something along those lines. So this one's a little bit different than that. So we've got V tan is going to be defined to be ds dt, but we're also going to say that omega is going to become d theta dt, and omega is what we call our angular velocity. And I'm using the word velocity, even though we know velocity is supposed to be a vector quantity, and we're going to give it a pseudo vector type definition in a second, but it is still a pseudo vector. So just be advised, we still use the term angular velocity, even though it's not technically a vector. But it's also called angular frequency. And of course, the units for omega ostensibly would be radians per second, but you could convert it to cycles per second, and a cycle would mean, of course, 360 degrees or 2 pi radians or something like that. But all that's completely fair game. You can call it cycles per second. You can call it revolutions per second. You can call it radians per second. All of those are acceptable. But to be honest with you, since S equals R times theta requires the theta to be in radians, then just know that in general, if you work with radians, it will always work in the equation, whereas sometimes the equation won't work if you use other units. Okay, so what we have now is V tangent is equal to R times omega. So this is another important equation. And remember what I told you about the tangent one. That's the one to give you an idea of what the velocity, the tangent velocity would be. If you went out into a large empty parking lot and you figured out a way that you could turn your steering wheel to just the right position, turning it left or right to just the right position, such that you repeatedly go over the exact same circle, okay, then you're actually in circular motion, and the velocity that your speedometer reads is in fact your tangential velocity. And if you hit the accelerator to speed up, that would be an increase in your tangential velocity, and that would be a tangential acceleration. Okay. Now, as a tangential acceleration, that might make you go so fast that v squared over r, which is the centripetal acceleration you need to maintain that circle, that might not be the appropriate amount of acceleration anymore. So you might have to completely reconfigure your circular motion now that you've sped up or even slowed down with that VTAN. But the main thing is I wanted to show you that there's also an A tangent, and that's what that is. It's the acceleration that your speedometer would exhibit when you speed up or slow down while traveling in a circular path. Uh, the next thing I want to do is I want to take the derivative of this equation. So I'm going to say d by dt of v tan. I'm going to go ahead again and assume the radius is a constant. So this is going to become r d omega over dt. And remember, omega is an angular velocity, and it would have units of radians per second. So the d omega over dt would be radians per second per second. And that sounds a little bit like an acceleration, and in fact it is. What you get from this is a tangent is equal to r times alpha. And again, that alpha could be radians per second per second. But the main thing is these are some fundamental equations that we'll use over and over again. For instance, one of the problems that you'll run into is if you consider a ball or a cylinder or something circular rolling down an incline, if you make the assumption that it rolls without slipping, then the equation v tangent is equal to r times omega becomes very relevant. Whereas if it actually slipped, the v tangent wouldn't link up with omega quite so well. So you got to keep that in mind, and you'll see as we apply it how that turns out to be. Now, we have these three equations that start us off in terms of kinematics of rotational motion, but I want to just go ahead and finish out the analogy. So these three equations are special. There's not an analog to them in the linear motion, but they're thought of as the conversion from linear motion to rotational motion. So they're just three additional equations that you'll be needing. You can imagine, of course, that the total velocity would be the v tangent plus the v centripetal or v center seeking or maybe even v centrifugal so that it goes out. Same thing with the acceleration. There's a tangential component, but the total acceleration uh, could probably be calculated by considering tangential acceleration, and then perpendicular to that is a centripetal or radial acceleration. Okay, so keep that in mind. But since they're at right angles, that just means they follow the Pythagorean theorem. So now let's go for the analogy. And the reason I make this analogy, well, that was nice of this stupid program. Uh, the reason I make this analogy is because it gives you a lot of power because once you realize the analogy, then you can work every problem in chapter 10 and chapter 10 related stuff exactly the same way you did in linear motion just by recognizing if you rewrote the question in linear motion, changing the appropriate units, you would know exactly what's omega, what's alpha, because basically once you change the units, it would be instead of alpha, you'd be saying A, and instead of omega, you'd be saying V, and so on and so forth. And by thinking about it that way, you can say, well, I know what equation I'd use in linear motion, and lo and behold, there's an analog to that in rotational motion. Okay, so one of the things we first started off with was just straight kinematics. And what we found was V bar was equal to x minus x0 over t. That's the average velocity, say. And there turns out to be an analog to that, and that analog is omega prime is equal to theta minus theta 0 over t. And you could write that as t minus t0 instead of just plain t. Either way is acceptable. Now, in addition to that, you know that the instantaneous velocity rather than the average is equal to dx dt. And of course, the rotational analog to that is v or excuse me, is omega is equal to d theta over dt. And then you could say, well, A average, sorry, I should be blue for linear. So A average would be V final minus V initial over time taken. And lo and behold, there's an analog to that. Alpha average is equal to omega minus omega 0 over T. And of course, A instantaneous, sorry, I was supposed to switch back to blue. A instantaneous is equal to dv dt, and guess what? That means alpha instantaneous would be d omega over dt. There I go again with the wrong color. So alpha is equal to d omega over dt. And it goes further than that. For instance, we had x is equal to 1 half at squared plus v0t plus x0. Well, the rotational analog of that is theta is equal to 1 half alpha t squared plus omega 0 t plus theta 0. We had v squared is equal to v0 squared plus 2a x minus x0. And of course, there's an exact analog to that. Omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. So we can see that basically the kinematics completely replicates itself. You can even go as far as doing the other average velocity equation, which is v0 plus v1 divided by 2 is equal to the average velocity. So in that case, I'd say v bar is equal to v plus v0 over 2. And of course, the rotational analog would be omega bar is equal to omega plus omega 0 over 2. And all these equations on the right hand side are only true for the acceleration being a constant. So A equals, well, actually, I should write that in red, I mean in blue, since we're talking about A here. So A equals a constant. But in red, that would mean alpha equals a constant. So hopefully that makes some sense. So you see that all the equations are just the same as we did before, and you can even use that as a descriptive way of figuring out how to solve a physics problem. You can completely change the wording. Well, you actually completely keep the wording the same, but you'll just change key units and key words. Specifically, like a problem will ask for the total angular displacement, and you just say, "What's the total displacement?" And it'll say the acceleration is a certain number of radians per second per second. You're going to replace that with the linear acceleration is a certain number of meters per second per second, and whatever equation you use in that reworded form of the problem. But with linear variables, you'd use the exact analog to those equations in the rotational variables. So everybody see how kinematically the analog works out? Anybody have any questions on it? Because I'm getting ready to jump to the dynamics part now. Okay, so the analogy continues, only we've got to introduce some quantities because it turns out that there's something analogous to mass, but it's not really exactly mass, so that's kind of weird. So we'll have to have a formula for that. There's something sort of equivalent to momentum, but it's kind of weird too. So little stuff like that. We can start off, for instance, with Newton's second law, and Newton's second law says the summation of the forces is equal to mass times acceleration. Now, that's the kindergarten version, of course. That's the version in which the mass is a constant, but doesn't apply if the mass is actually varying. So I'll address that too in a second. But you can immediately figure out what the rotational analog is by realizing what the rotational analog of the variables are. So in place of the summation of forces, we're going to do the rotational analog to a force. And some of you might already know this. Anybody think you know what the rotational analog of force is? It's a T word, and there's a type of wrench that has that word as the first word of it. So we use the symbol tau, and that represents torque. So torque is quite a bit different than force. I'm going to give you a formula for that in a second, and that of course is a formula that you don't have an analog for because we had to define the torque. But the summation of the torques is equal to not mass, but specifically I, and not A, but specifically alpha. Okay. Now, in addition to that, we have to figure out what the poop I is and what the poop torque is and all that good stuff. So I will tell you that torque can be written as R cross F, which is a nice way of writing it. If you want to talk about the magnitude, it can be R perpendicular times F, or it can be F perpendicular times or it can be R times F times the sine of the angle between the R vector and the F vector. Now, the R vector is what we call a lever arm vector, and that would point from the center of rotation to the actual point of application of the force. So you'll see that in some examples, and to make sense of it. But definitely write down somewhere that r is a lever arm vector. Now, in addition to that, we can say I is equal to the summation from I equals 1 to n of m sub I r sub I squared, where r sub I is really the distance perpendicularly from the axis of rotation of the body. And therefore, you're taking the mass times the distance squared for each of those individual masses and adding them up. But in the case where it's continuous material as opposed to discrete material, it becomes the integral of r squared dm. And of course, we still have the usual dm equals lambda dl, r it equals sigma dA, r it equals rho dV. So those things obviously come in handy and are necessary for us to make sense of the left equation matching the right equation, because we don't really understand what torque is until we have a definition. And we don't really understand what I, the moment of inertia, is until we have a definition. So I'll just label this moment of inertia. And that's what we call it in physics. This right here is called the torque. And this vector here is called the lever arm. Okay. And again, the lever arm points from the center of rotation of the object to the point of application of the force when you go to calculate the torque. And then, of course, you really only need the component of the force perpendicular to the lever arm, or you only need the component of the lever arm perpendicular to the force, or you have to calculate r times f times sine of theta, where theta is the angle between the two vectors when they're tail to tail. So you literally have to force them to be tail to tail by moving your vectors around to get them in that position, and then figure out what theta is, and then you can calculate r times f times the sine of theta. Now, there's another version of Newton's second law, and that other version of Newton's second law is the summation of the forces is equal to dp dt. And of course, we had that p is equal to m times v, where v is a vector quantity. Well, there's a rotational analog to this as well, and it's the summation of the torques is actually equal to dl dt, and L is called the angular momentum. And one way of calculating it is R cross P. And of course, P is equal to mv, as we knew before. Okay. Now, there's also another way of talking about the angular momentum, and that is the magnitude of the angular momentum L is just equal to I, the moment of inertia, times omega. Now you see how L is a rotational analog to P. P is mass times velocity. The rotational analog to mass is moment of inertia, so you see the I's there. The rotational analog to velocity is omega, so you see the I's there. And in fact, you could ultimately define the vector quantity, as we already hinted at before, by making omega into something like a vector. It would be a pseudo vector, but in doing so, it would just become L equals I times omega. So, any questions on that? Now, your book does talk specifically about when you can use the summation of torques equals I times alpha. You definitely need to read that stuff over and understand it. Ask me questions if you have them. But this is an idea that hopefully will help you quite a bit in figuring out how to solve all these physics problems. So we've introduced some new variables. We've introduced the angular momentum. I should go ahead and label that too. So that L is your angular momentum. The I, like we said, is moment of inertia, and so on and so forth. But this is sort of well, it's almost the complete litany of equations you need. Let me give you one more, and that is kinetic energy K is equal to 1/2 mv squared. But there exists a kinetic energy of rotation, and that's 1/2 I omega squared. You can see that it even holds up to this new equation, 1/2 mv squared. The analog to m is I, the analog to v is omega, and lo and behold, it fits that formula as well. All right. So that is more or less a complete synopsis of all the equations that we'll be using. We've got to remember that, of course, r is the distance measured perpendicularly from the rotation axis to the point at which we wish to calculate dm, for instance, or at which we wish to calculate the torque, all that good stuff. So you got to keep that in mind. Let's go ahead and look at some examples. And again, we're going to be using the examples from the book. So example 10.1 is a good start. So again, this is from your book. It says a bike wheel rotates 4.50 revolutions. How many radians has it rotated? So a bike wheel rotates 4.50 revolutions. Now, revolutions might not sound like one of the variables that you just learned, but it is in fact theta. Theta equals 4.50 revolutions. Now, remember, a revolution is a complete circular trajectory or path, if you will. So once you go, you've completed one revolution, two revolutions, three revolutions, so on and so forth. So you can sort of see that a single revolution should be 2 pi radians. That's one of the things I said. I didn't use the word revolution, I used the word cycle, but revolution obviously fits. So in this case, we're going to say solution, and the solution is going to require the fact that 2 pi radians is equal to 1 revolution. Therefore, theta equals 4.50 revolutions. I'll put that over 1 because it's a unit conversion essentially. And then I'll say that 1 revolution is equal to 2 pi radians. And therefore, we have theta is going to be 4.50. Now, obviously, you can keep this in terms of pi, and that would be nice. And we'd get 9.00 pi radians. And that works fine. That is a correct answer. But in this case, I'm going to go ahead and work it out into a decimal form. So I'm going to say 4.50 times 2 times 3.14159. And that gives me 28.27 radians. Of course, they gave me 3 sig figs, so I underlined the 7 because that is an extra digit. Straightforward, right? Anybody have any questions on that? All right, let's look at example 10.2 now. Now, this one's about a bird of prey. It says birds of prey in radians. A particular bird's eye can just distinguish objects that subtend an angle no smaller than about 3 times 10 to the negative fourth radians. A, how many degrees is this? And B, how small an object can a bird just distinguish when flying at a height of 100 meters? Okay, so I'm going to say delta theta because it really is a difference in theta that we're looking at here. You can this is one of the things we use in astronomy, for instance, to try to get an idea of what the eyeball's angular resolution is, and we think how large of a change in the angle must the positions make. In other words, from let's say the tail of a rabbit to the nose of a rabbit, if you're trying to trap or capture a rabbit, what angle does the theta have to sweep through to go from the tail of the rabbit to the head of the rabbit? Uh, that angle is a measure of what we call your angular resolution. So, for instance, if you can distinguish the head from the tail, then whatever angle separates them, that angle is bigger than your angular resolution, meaning you can see better with better definition than that angle suggests. So we often use it as what's the smallest angle between two objects where you can distinguish them as two objects. So the analogy that I normally tell my students is if you've ever driven late at night, like down the interstate or whatever, and you look off in the distance when a car, especially when the road's particularly straight, you'll see a car coming. And when you first see them, it's really hard. You can't tell whether it's actually a car or a motorcycle because it could be just one light uh, because that's what you first see if the vehicle is really far away. But as the vehicle gets closer and closer, if it is a car, then that one light will separate out and make two lights. And once you can actually see it as two lights, the angle between the center of the one light and the center of the other light is your angular resolution of your eyeball. Okay. So that's hopefully that's enough to help you with this. So in this case, we say that the eagle can see or has a angular resolution of 3 times 10 to the negative fourth radians. Now remember, a radian's a big angle. It's like 57.3 degrees or something. So that's pretty huge. So 3 times 10 to the negative fourth. 10 to the negative fourth suggests it's small. It's like 0.000 and then a number. But again, the number was pretty big to begin with. So it's not necessarily as small as you think. In part A, they want to know how many degrees. Oops. And then in part B, they want to know how small of an object can the bird just distinguish when flying at a height of 100 meters. I'm going to call that height an R, and that's going to make some sense in a little bit, but I'm going to say it's 100.0 meters with that zero after the decimal place underlined so that I can assume for my own happiness that the measure is actually made to 3 sig figs. And for r equal 100 meters, what is the size distinguishable? Whoa. So that's the problems we're going to work. So let's start off with solution. Uh, Pi radians is equal to 180 degrees. That'll come in handy. And we're also going to realize that S is equal to R times theta. That might come in handy. So for part A, I'm going to go ahead and say that delta theta is equal to 3 times 10 to the negative fourth radians. This is a unit conversion, so like I taught you before, you want to put that over 1 because we're getting ready to multiply by a fraction, and it's very easy to make a mistake and misunderstand whether the 3 times 10 to the negative fourth is the numerator or denominator. So if you put it over 1, you can automatically see it's the numerator. But now what I got to do is get rid of the radians, so that means I'm going to divide 3 times 10 to the fourth by pi, and that, of course, causes the radians to cancel out. And then, of course, I have to take that answer and multiply it by 180 degrees. So 3 times 10 to the negative fourth times 180, and then I'm going to say divided by 3.14159, and that gives me 0.0172 degrees. Now, technically, the 3 times 10 to the negative fourth was only 1 sig fig, so the 7 and the 2 are not sig figs. So that angular resolution that the eagle has is roughly 0.02 degrees, 200ths of a degree. That's pretty small. I mean, that's pretty good. Now, in this other part, it's a little tricky, but what we can do is we can imagine the eagle's eye is really, really far away. And of course, this is a grotesque misrepresentation of delta theta because delta theta would be really, really small, but I'm trying to show it big. But what we could do is we can say R is this distance, but it's also this distance. And in fact, we can use this to help us figure out exactly what this arc length is because even though it's an arc length, which is a curve distance, right? The angle is so small that the curve distance is probably very, very close to the chord distance. That's the word that you use for instance, this quantity measured from here to here. So chord length, and I think they spell that Chord. Correct me if I'm wrong, but definitely check that out. So chord length is approximately equal to arc length when we're dealing with such a small delta theta. Okay. So we can say S is equal to R times delta theta. And then from that, we're going to say RS is equal to 100.0 meters times delta theta. Now, S equals R times theta requires us to have it in radians, so I can't use that 0.0172 degrees. I actually have to use the radians, so that's 3 times 10 to the negative fourth radians. And obviously, this will become 3 times 10 to the negative 2. Whoa, there goes my stupid program automatically jumping to making better drawings. So this is 3 times 10 to the negative 2 meters. And in this case, that means it's about 3 centimeters. So at 100 meters away, which mind you is on the order of 300 plus feet, at 300 plus feet away, it can it can see an object that's only 3 centimeters in width or length or whatever. So that's a pretty good amount or a pretty good eyesight, if you will, what we call it, pretty good resolution. Anybody have any questions on that? All right. Now we're going to go ahead and move on to ah, there's a nice conceptual example. It's conceptual example 10.3. I'm going to sort of read this to you and let you think about it a little bit. Feel free to answer you can type in the chat or you can just blurt out your answer, whatever you want. It says, is the lion faster than the horse? On a rotating carousel, there's that word I was trying to think of earlier, and merry-go-round was the one that I kept coming up with, but I was like, I don't call that a merry-go-round because I'm picturing a merry-go-round as the one that you manually push yourself on a playground, but technically, probably they're both the same. So, on a rotating carousel or merry-go-round, one child sits on a horse near the outer edge, and another child sits on a lion halfway out from the center. Which child has the greater linear velocity? Which child has the greater angular velocity? So this is kind of a weird concept, but it's something you've got to get. So if you think of the carousel as the top of this Rubik's cube, what you have to remember is a line going from the center of the Rubik's cube to that corner, for instance. That could be the line from the center of the carousel to the edge. And of course, the edge is where the horse was, and the lion is only halfway out. So, what I want you to do is imagine right now that line, which goes from the center through the lion and then through the horse, that is pointing straight at the camera. Okay. Now, if I rotate it like this about that axis right through the center, then what you're going to see is that line moved through the exact same angle every part of it. So that meant the lion moved the exact same angular distance, which we measure like in degrees or radians, as the horse did. So we can already guess that the angular velocities for the lion and the horse are identical. But the linear velocity, what we call the tangent velocity, that is actually very different. So let me show you exactly what we mean on that one. Or actually, I don't even need to show you. So we know V is equal to R times theta, and theta, or excuse me, V is equal to R times omega, and omega is the angular speed, right? But the R is different for the horse than it is for the lion. The R is like capital R for the horse. So V, the linear velocity of the horse, V sub H, is equal to capital R times omega. And whatever omega is, that's the same for the lion and the horse. Now, if you want to know the velocity of the lion, you're going to say V sub L instead of V sub H, which is what we had for horse, is equal to not capital R, but parentheses capital R over 2 times omega. So you can already see that that R over 2 for the lion means the lion's going to be going half the speed of the horse. This is also relevant if you've ever water skied behind a boat, that sort of thing. For instance, when they're dragging you on the rope, normally you're straight behind the boat skiing like this or whatever. But when you swing out to the outside during a turn, for instance, then you actually go out on a larger radius of curvature than the boat is. Maybe the boat's turning on a radius of curve that's maybe 25 or 50 meters, and then you're another 10 meters further out than that. If you are keeping up with the boat so that you're literally right beside the stern of the boat at all points in time, then your angular speed and the boat's angular speed are identical. But because the boat is only a 50-meter radius turn and you're another 10 meters larger than that, that means you're going to go faster than the boat. And that's actually resulted in people maybe not understanding that and getting way more injured than you should have gotten just by not realizing that you're going so much faster than the boat when you swing out to the side like that. Anybody have any questions on that? I know that water skiing is a little esoteric, but it's something from my past, so I tried to use it. All right, so let's look at this. This is example 10.4, and I'm going to write out example 10.4. And it says angular and linear velocities and accelerations. A carousel is initially at rest. So a carousel, like the same thing we were talking about a second ago, is initially at rest. At t equals 0 seconds, it is given a constant acceleration. At t equals 0 seconds, it's given a constant acceleration of of alpha is equal to 0.060 radians per second every second. Now, your book's writing this as radians per second squared, but just like we did in linear motion in chapter 2 and 3, I suggest that you read it as radians per second, or radians per second every second. And it increases its speed so that the velocity increases. I'm going to read it again after all this. So it increases over 8.0 seconds. In other words, we're letting this acceleration go on from t equals 0 to t equals 8.0 seconds. And what they want to know is that t equals 0, determine the magnitude of the following quantities. So what they want is A, what is the angular velocity of the carousel? So omega equals question mark at t equals 8.0 seconds. B, they want to know the linear velocity of the child located 5.5 meters from the center. So, child at r equals 5.5 meters. What we want to know in that case is the linear velocity, which is what we call tangential velocity. And then part C, the tangential linear acceleration of the child. So A tangent equals question mark 4 to the child. That's part C. Part D, the centripetal acceleration for the child. And part E, they would like to know, again, I'm going to read this question again, so don't worry too much. E, the total linear acceleration. So A total of the child. So again, a carousel is initially at rest. At t equals 0 seconds, it is given a constant angular acceleration of alpha equals 0.060 radians per second, which increases its angular velocity for 8.0 seconds. At t equals 8.0 seconds, determine the magnitude of the following quantities. A, the angular velocity of the carousel. B, the linear velocity of a child located 5.5 meters from the center. C, the tangential linear acceleration of that child. D, the centripetal acceleration of that child. And C, the total linear acceleration of the child. So that's what we're trying to solve here. I will write down solution. Anybody have any questions before we get started on this? Anything bothering you? Okay. So the equations that we want to use might not be obvious to you, but notice how I can reword the problem. I can say an object is initially at rest. Before it said a carousel is initially at rest. An object is initially at rest. At t equals 0 seconds, it is given a constant acceleration. Notice I left out the word angular. Acceleration of a equals 0.060 meters per second, which increases its velocity, left out angular again, for 8.0 seconds. At t equals 8.0 seconds, determine the magnitude of the velocity of the carousel, the linear velocity, or in this case, the velocity of the kid, so on and so forth. So, what we're thinking is what would, in that situation, using those words from linear motion, what equation would we like to find? Well, we want to find the final velocity. And what we know is that V is equal to V0 plus AT, which might not be that familiar to you, but let me remind you, it is, in fact, this average acceleration equation, except average is equal to the instantaneous acceleration whenever A is a constant. And that's what's going on here is the constant acceleration. So the fact that we would use V equals V0 plus AT tells us that we can also use omega is equal to omega 0 plus alpha t. So that comes in really handy, and that's of course mostly for part A because they want to find out the angular velocity of the carousel, and then the once we have the angular velocity, we can use V equals r omega to figure out tangential velocities, and we can use A is equal to r times alpha to figure out tangential accelerations, but we can also figure out centripetal acceleration, which is A centripetal is equal to v squared over r. Okay, so that should be all we need. Let's start off with part A, the angular velocity of the carousel. So omega is equal to omega 0 plus alpha t, but it was initially at rest, so that means 0 radians per second plus alpha, which is 0.060 radians per second every second times 8.0 seconds. And obviously, 8 times 6 is 48, so this would be 0.480 radians per second. So omega carousel is equal to 0.480 radians per second. And they didn't explicitly tell me what unit to use, so I'm going to go on the assumption that that one's just fine. And that's the way they recorded it as 2 is radians per second. So now we're going to look for the linear velocity of the child, which is, as I told you, it's the tangential velocity. So B, V tangent equals V linear is equal to R times omega. We've got omega already, so we can say that V linear is equal to 5.5 meters times 0.480, oops, radians per second. So 5.5 times 0.480 gives me 2.64. Now there's only two sig figs, so I have to underline that 4, but this is 2.64 meters per second. So that's the linear velocity of the child. Now for part C, it says they want to know the tangential linear acceleration of the child. Well, oops, got a person trying to come in. Let me click that real quick. So it says the linear velocity of the child. We did that. Part C says the tangential linear acceleration of the child. So what we know is the acceleration is A equals R times alpha. So A is equal to R times alpha. That means A linear, which is what they're asking for, is 5.5 meters times the angular acceleration, which is 0.060 radians per second every second. And if I multiply that by 5.5, I get 0.33, carrying one extra digit, and that is 0.330 meters per second per second. Now, notice something here. I just dropped that radian. You can do that. You can drop radians at any point, and you can add radians in at any point if you need, because a radian is technically speaking, it's just a pure number. Because remember, S equals R times theta is the definition of theta in radians. And if you solve for theta, you get S, the arc length, divided by R, the radius. And obviously, you're supposed to use the same units for S and R. So if you take the S in centimeters and divide it by the R in centimeters, you get just a pure number. So a radian really is a pure number. So if need be, you can throw a radian in. If need be, you can erase a radian. So instead of me writing meters radians per second, I just wrote meters per second. So that should be A ln is equal to 0.330 meters per second every second. That's the answer to part C. Any questions there? Okay. Now that we have that, part D wants to know the centripetal acceleration for the child. So we can say d a centripetal is equal to v squared over r. And this is where we got to remember that v in the formula v squared over r is the tangential or linear velocity. So we happen to already know that. That's 2.64 meters per second. Notice how I am carrying the 4. That's the whole point of keeping one extra sig fig or one extra digit beyond the sig figs, so that you only round once each time. And then this is going to be divided by 5.5 meters. So I take 2.64 and I square it, and then I divide that by 5.5, and I get 1.267. And that turns out to be meters per second every second is equal to a centripetal. So I can box that off as well. And now, of course, we only had two sig figs, so the 6 and the 7 are not sig figs. So let me underline them just to remind us of that. Now for part E, it wants to know the total linear acceleration. So let me show you exactly how we go about doing that. What we have here is, let me draw an arc length. Okay. And what we have is a linear acceleration and then a centripetal. And of course, they have to be at a 90-degree angle. And what that means is we can complete the parallelogram and say that this is the actual total acceleration. So we can say A total is equal to the square root of A length squared plus A centripetal squared, like that. And of course, that's equal to the square root of 0. Whoa, there, my calculator, my stupid. 0.330 meters per second every second. That quantity is going to be squared plus 1.267, carrying two extra digits here, meters per second. Of course, when you square this, this becomes meters per second, meters squared per second to the fourth. But then you take the square root, that becomes meters per second squared again. So I take the 0.33 and I square it, and I add to it the 1.267 squared. Just for the record, 0.33 squared is 0.10, so we only get it to not the tenths place, but the hundredths place. And 1.267, when I square that, that is only supposed to have two sig figs, so that's only to the nearest tenths place. So when I add the two, I can only keep it to the tenths place. And when I added them, I got 0.33 squared plus 1.267 squared is 1.714. So this is the square root 1.714. And those are two extra sig figs, and that's meters squared per second to the fourth, like that. So we can say A total is the square root of that. And obviously, we only have two sig figs. So now I can take the square root of 1.714 raised to the 0.5 power. Ooh, I don't know where that came. Oh, 1.309. Let me double check. Yep, 1.309. So this is going to be 1.309. Those are two extra digits there. Meters per second is the total acceleration. the total linear acceleration of the child. Anybody have any questions on that? So just checking the answers, they got 0.48, they got point 0.2 or 2.64 or 2.6, they got 0.33, they got 1.27, and they got 1.31, which is the same thing we got, only they cheated by adding an extra sig fig. If you wanted to, you could also figure out what that angle is, of course. I don't think they asked anything about that. Let's double check. Yeah, the total linear acceleration child. So you could actually figure out what that angle is. You could, for instance, find out this angle right here by taking the inverse tangent of A linear over A centripetal, and that would give you, your book is saying about 15 degrees, but that's really what the vector means when you figure out that it has a centripetal component as well as a tangential component. Any questions? All right. Well, let's see. I think this might be a good time for you guys to go ahead and take a break. It's 6:46. Let's come back at 6:56. So I'll give y'all a 10-minute break. I know I can usually forget to give that to you, so I apologize, but I'm giving it to you now. And let's go ahead and make it 6:57. I'll be here if anybody has any questions, but you can come back at 6:57. All right, so let's go ahead and get started. We have example 10.5 that I'm getting ready to work next. And example 10.5 says, given omega as a function of time. Remember, omega is the angular velocity. It's what we normally measure in radians per second, but you could also measure it in revolutions per second, cycles per second, degrees per second, uh, stir radians per second, all sorts of crazy stuff. So, anyways, given omega as a function of time, a disk of radius capital R equals 3.0 meters rotates at an angular velocity of omega equals parenthesis 1.6 plus 1.2 t close parenthesis times radians per second. So that's a way of just writing out exactly what the units of omega come out to be. And in order for that to be true, the numbers, all the stuff inside the parentheses has to have no units whatsoever, uh, because otherwise they'd have the angular velocity would have the units of whatever's inside the parentheses times radians per second. But we know omega is supposed to have radians per second. And in fact, they tell us where t is in seconds. So that tells you the 1.2 must have units of reciprocal seconds because it's multiplying by t in seconds. And the only way you could get no units is if the seconds cancel out in the top and bottom. That also means the 1.6 has no units. So the 1.6 has no units. The 1.2 has a unit of reciprocal seconds. And the t, of course, has units of seconds. So it says a disk of radius r equals 3.0 meters rotates at an angular velocity omega equals parenthesis 1.6 plus 1.2 t close parenthesis radians per second, where t is in seconds. At the instant, at the instant 2.0 seconds, determine a the angular acceleration, b the speed v, and the components of the acceleration of a of a point on the edge of the disk. Okay, so that's what we're trying to solve here. Write down solution. Now, the equations we're going to need here are obviously, since one of the things they're asking for is to calculate alpha, and alpha is d omega over dt. So we're going to need that. We're also going to need the components of the acceleration, and we know the components of the acceleration are a is equal to r times alpha. But we also have the other equation that a centripetal is equal to v squared over r. Now, here's a good time to use the equation v equals r omega because you could put in r omega in place of that v, and you'd end up getting r squared omega squared over r, so that's r omega squared, which is a little more convenient way of writing and calculating centripetal acceleration in this case. Now, we also need to know the velocity, and that requires us to use v is equal to r times omega. So that should get us everything we need. Let's start off with A, where we're supposed to calculate the acceleration alpha, the angular acceleration. So alpha is equal to d omega over dt, which is d by dt of 1.6 plus 1.2t. And of course, that comes out in radians per second. We're just going to leave that for right now. Not a big deal. The derivative of 1.6 is just the derivative of a constant, so that's 0. But the derivative of 1.2t is just 1.2. And now that we've computed that, it's a good time to write in that the units are radians per second. So the actual angular acceleration is alpha is equal to 1.2 radians per second. I'm going to go ahead and circle that because that's part A. Well, I'm going to box it, not circle it. Now for part B, they want to know V, and what we know is V is equal to R omega. In our case, we're using the capital R, but we can figure out exactly what the omega is at t equal 2 seconds. So at t equals 2.0 seconds, omega of 2.0 seconds is equal to 1.6 plus 1.2 times 2.0. I'm leaving the units off here, but notice the 1.2 would be seconds to the negative 1 power as its unit, and the 2.0 would have units of seconds, and the 1.6 would have no units whatsoever. So what we're going to do here is take the 1.2 times 2.0. That gives me 2.4, and I'm going to add to that 1.6, and that gives me 4. So the angular velocity is 4.00, and that turns out to be in radians per second. So that's the actual angular velocity, but we didn't need that. What we needed was v, but we couldn't get v without omega. So now I can say v is equal to 3.0 meters times 4.00 radians per second. And obviously that gives me 12.0. And again, we can just throw away that unit of the radian. And that turns out to be V equals 12.0 meters per second. Oops, that's supposed to be V, like that. I'll box that off, and that happens to be part of our answer for part B. Now, for part B, we were supposed to find V, but now we're supposed to find the components of A. So the components of A, of course, are A tangential is equal to R times alpha. And we also need a centripetal, but in this case, I just showed you a neat new way we can calculate v squared over r, where I'm just going to use r omega squared. So a tangent is going to be 3.0 meters times alpha. We already found out that alpha was 1.2 radians per second. Oh, that was supposed to be radians per second, by the way. Everybody make sure you correct that part A up there. I wrote radians per second and I didn't even think, but it's supposed to be radians per second per second. And the reason that is, of course, is you have 1.2 having a unit of seconds to the negative 1 power. And then the whole quantity in parentheses had units of radians per second. So radians per second times 1.2 per second gives you radians per second per second. So anyways, this is radians per second, like that. And of course, 3 times 1.2 is 3.6. And that's 3.60. Now I can drop the radians again. It's going to be meters per second. Every second is atan. I'll box that off because he asked for the components. That's one of them. Now I'm going to say a centripetal is equal to r omega squared. R is 3.0 meters, and omega we found was 4.0. No, that was v. Oh yeah, omega was 4.0. So it's 4.00 radians per second was omega. That's from this calculation right here, in case anybody forgot. So 3 times 4 again, because it's omega squared. So 4 times 4 is 16. If I multiply 16 times 3, that'd give me 30 plus 3 times 6 would be 18, so that'd be 48. So this gives me 48.0, and these units are meters per second is equal to a centripetal. So those are our two components. Again, if we wish to figure out like vectorially what they'd look like, let me go ahead and draw it. So this is a piece on the edge of the disk. Okay. Now what we have is the object, the edge specifically that they were talking about, has a tangential component of acceleration that is 3.6. So I'll write it this way. And notice how I drew it tangentially. In other words, it's tangent to or parallel to the arc at that particular point, and that is 3.60. And that's an extra sig fig, the zero. I forgot to underline it before, but that's meters per second. And now, in addition to that, we have a radial component that points inward, and that one's quite big. Uh, this is still scaled too small. In other words, this red vector that I drew radially inward should actually be quite a bit longer for the scale, but this gives you a rough idea anyways. So I'll complete the parallelogram because that's the way you add two vectors that are in tail-to-tail configuration. So the actual answer will be this acceleration right here, a total. And of course, we can figure out what that angle phi is as well. So first off, I'll calculate the magnitude of a total. That's going to be equal to the square root of 3.60 squared plus 48.0 squared. Of course, I left off the units just because it's a pain in the butt to write all that stuff. But I have two sig figs in both cases, so 3.6 squared gives me 12.96. So that means it's only good to the ones place. And 48 squared gives me 2,304. That means it's only good to the hundreds place. So we're going to add 2304 plus 12.96, and that's going to give us the square root of 2316.96. But again, we technically only have the 2 and the 3 that are sig figs. So we are going to get basically two sig figs out. I'm going to take the square root of 2316.98. So I'm raising it to the 1/2 power, and that gives me 48.13. And you can see it's essentially just 48 because 48 is so much bigger than 3.6. But that's the total. It's 48 meters per second. Every second is a total. And phi, the angle that the acceleration vector is ahead of the centripetal acceleration vector, is given by the inverse tangent of opposite over adjacent. That would be 3.60 over 48.0. So if I take the inverse tangent of 3.6 divided by 48, I get 4.29 degrees. So you can see again, that's a very, very small angle, and that's indicative of the fact that the tangential acceleration is so small compared to centripetal acceleration. Anybody have any questions on that? Now, I did extra there again because I wanted to show you what I showed you on the previous one, which is once you have the two components, a tangential component of acceleration and then a centripetal component of acceleration, what is the total acceleration and how do record that, for instance? So hopefully that gives you a little bit of insight into that. You could literally write a vector A as if it has a component 3.60 in the v direction. So you could say 3.60 times v hat plus 48 times negative r hat. So negative 48 r hat because r hat is radially pointing outward, meaning r hat is a unit vector that any vector with a hat on it we interpret to be a unit vector. And the r means radial, and radial normally means from the center of like your radial tire to the treads on your radial tire, that's radially outward. This centripetal acceleration is radially inward, so we'd write it as 3.6 meters per second v hat minus 48 meters per second r hat. Notice the negative is what took care of the direction there. Any questions on that? Okay, so in section 10.2, they do talk about the vector nature of angular quantities. So what we do to define the angular vector related to omega, for instance, is we imagine like a disk rotating. So let's say the top of this little pencil sharpener here is a disk. If that's rotating this way, okay, then what you could do is take your right hand. It's important. We use right hands a lot in mathematics, and this is one of those cases. We're going to take our right hand and make our fingers curl in the direction that the disc is rotating, and then our right thumb points in the direction. Now, let me give back up and give you a reason for that. If you wanted to represent this disc rotating this way, and you wanted to do it with a vector that was in this disk, there is an infinity of vectors. There's that one, 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 there's that one. All of those vectors are fair game, and I can't make a good reason for choosing one of those over any other one of those. So it's really, really not useful to think about a omega vector in the same plane as the object that's rotating. So that leaves us to let's choose perpendicular. Well, if the surface, like in this case, we're talking about a rotating disk, therefore this surface is the thing that's rotating. If we choose a vector perpendicular, we only have two choices. We have that one and we have that one. So if you attach a right hand rule to it, then that can tell you exactly which one to want, and therefore that's what we did. So the omega vector associated with this thing rotating this way is a vector that points upward and is perpendicular to, it's actually parallel to the rotation axis. That's a good way of thinking about it. But it has to be consistent with the right hand rule where your fingers are curling in the direction of rotation and your thumb points in the correct direction parallel to the rotation axis. So that is the omega vector. Your book gives you a nice picture of it. You can imagine alpha is going to be similarly defined, stuff like that. But what they do is they point out that it's a pseudo or axial vector. And remember, pseudo means not. So someone once heard someone say that something was a pseudoscience, and they took that as a compliment, meaning that it was a type of science. And no, it's not. Pseudoscience is the essentially the opposite of a science. So similarly, pseudo in terms of vectors is not a real vector. It's a pseudo vector. So, anyways, if you actually consider this plane, this little disc on the top of this pencil sharpener as the thing that's doing the rotating, we see that omega points this way. right? Now, if you look at a mirror image of that, you'd find that the vector points in the left-handed direction in the mirror image. That's what makes it a pseudo vector because in a mirror image it should still be the same vector, but you can see that in the case of the image, it's actually the part of the disk that's rotating is closest to the mirror and going away from the mirror, whereas the original image, the part of the disc that was rotating went from close to the mirror away from the mirror as well. But away from the mirror outside means the right hand rule gives you this way, whereas away from the mirror inside gives you the right hand rule doing that way. So the fact that the omega is this way in the mirror and this way in the original tells you that it's a pseudo vector. So hopefully that helps you a little bit. Let's go on to section 10.3, which is where they're talking about the equations of kinematics. So let's do some straightforward examples. I'm going to start off with example 10.6. Again, if you have any questions, make sure you ask me. So this is example 10.6. And example 10.6 says centrifuge acceleration. I almost thought they were saying centrifugal, and I realized I was mispronouncing it. So centrifuge acceleration. So a centrifuge, for instance, you might know of from the medical field, or you might have recently heard about it regarding nuclear weapons. So we use centrifuges to take either a liquid or a gas. Of uranium and separate out the heavier isotopes from the lighter isotopes so that we can get the one that has the punch, the uranium 295, if I remember correctly, has the actual nuclear punch that we need for it to make a nuclear weapon or nuclear fuel rods for power, or yeah, fuel rods for a power plant or something like that. So, anyways, it says a centrifuge rotor is accelerated for 30 seconds from rest to 20,000 RPMs, revolutions per minute. So, omega zero is equal to zero. T is equal to 30.0 seconds. So I'm saying that the 3 and the 0 are sig figs by putting that dot 0 with the underbar after it. And the final omega is 20,000 revolutions per minute, which are called RPMs. That's the same RPM that you've seen in your car. If you have a tachometer in your car, that's the same thing. It just means revolutions per minute. They want to know A, what is the average angular acceleration? So A, alpha bar equals question mark, and they want that in radians per second. And then for part B, they want to know through how many revolutions has the centrifuge rotor turned during its acceleration period, assuming constant acceleration. So assume alpha equals a constant. And what we want to know is theta equals question mark because theta is the variable that we use for distance traveled, or in this case, revolutions. So they want to know theta in revolutions. My stupid program keeps jumping to things that I didn't tell it to. So let us begin. So what we have here is a desire to calculate alpha bar, and alpha bar is given by omega minus omega 0 over t. Of course, we could also use alpha bar equals omega plus omega 0 over 2 if it's constant acceleration, which they did tell us to use. So actually either one of those will work. And then in part B, they want us to find, assuming alpha equals a constant, they want to know theta. And theta I can use as 1/2 alpha t squared plus omega 0 t plus theta 0. And that's a really good equation we can use. We could also use, I don't know, V theta equals omega bar t. We could use that. All sorts of different things. We could use omega squared is equal to omega 0 squared plus 2 alpha theta minus theta 0. All these are different things we could use. Obviously, we haven't calculated an average omega, so that middle one's probably not that helpful. But we can go ahead and start with this by working in part A. So, anybody have any questions before I move on to calculate this? Okay. So, what we want to know here is what is the average angular acceleration? And the average angular acceleration is basically where we try to calculate alpha bar, which equals omega minus omega 0 over t. Now, omega 0 was 0, and omega is actually RPMs, but we actually want alpha bar in radians per second. So we really need to go ahead and convert this to radians per second. So when I say 20,000 revolutions per minute, and then I go to use 30 seconds, there's all sorts of problems with this. For starters, it's in revolutions. We want radians. And for as a second case, we have it per minute and we want it per second. So that's a problem. So what I'm going to do is I'm going to take this 20,000 revolutions per minute and I'm going to multiply it by 1 minute is equal to 60 seconds. That'll convert it to revolutions per second. And then I'll go ahead and show that by canceling out the minutes. And then I'm going to use the fact that one revolution is 2 pi radians. So I'm going to go ahead and put one revolution in the bottom and 2 pi radians in the top, like so. And in this case, that revolution cancels out with this revolution down the bottom, and that does give me radians per second. Now I have to do the minus omega 0, but omega 0 was 0, so I'll say minus 0 radians per second. And then I've got to divide all this by 30.0 seconds. So when I go to work this out, it's 2 times 10 to the fourth. That's what 20,000 is. Divided by 60, and then times 2 pi, like that. And now that gives me in the numerator 1047.20, and that's radians per second over 30.0 seconds. And that gives me 34.9 radians per second every second is equal to the average angular acceleration. Uh, we did only have 2 sig figs for the 30 seconds, so if I assume that I had at least 2 sig figs on the 20,000 revolutions per minute, then the 9 and the 1 should not be significant. Anybody have any questions on that? Uh, uh, hmm, I must have made some careless mistake on the. I'm going to try to calculate my math again. The 20,000 divided by 60, and then I multiplied by 30. I think maybe I screwed up on my order of operations, but 2 times 10 to the fourth should still work. So 2 times 10 to the fourth divided by 60. That's 1 minute on the top and 60 seconds on the bottom. So that's going to give me 333 revolutions, or excuse me, revolutions per second. So basically, what I'm doing here is I calculated 34 radians per second, but your book is saying it's 70. So I clearly made some kind of arithmetic error. I want to see what's going on. So what I'm going to do is say 20,000 revolutions per minute times 1 minute is equal to 60 seconds. Gives me, in this case, 333 revolutions per second. Now I've got to take this 333.3 revolutions per second and convert it to radians per second. So I'm going to take this 333 and I'm going to say one revolution in the denominator is equal to 2 pi. Oh, I think I see why. I think I multiplied by pi instead of 2 pi. Yep, that's exactly what I did. Okay, cool. I was afraid I'd done something really stupid, like an order of operations things, but I hadn't. So this will work. 333.33 times 2. Okay, calculator's being a butt. So I'm going to say it's answer times 2 times 3.14159. So in this case, I get 2094.4 radians per second. So if I plug this in instead of that, then let's see what we get. 2094.4 divided by 30. Oh, I found another problem I did earlier. Okay. That gives me 69.81. So I'm going to go back in here and say this answer is 69.81 radians per second is the average angular acceleration, and that's consistent with what the book had is 70. So thankfully I caught that. Remember, you guys are supposed to be sort of calculating along with me. So ideal scenario is when I make a mistake like that. In this case, it turned out I just forgot to multiply by 2 because it's times 2 pi instead of pi. Y'all would have easily caught that and kept me from doing that. And it also is more helpful to you to be doing the calculations in real time. So anyways, there goes the A part. Now in part B, they want to know, assuming alpha is a constant, through how many revolutions does it go? As I told you before, you can in principle work every equation, every problem using theta and radians. But sometimes you can actually use the units you want. So what I will do right now is I'm going to use one of our expressions. I'm going to use theta is equal to 1 half alpha t squared plus omega 0 t plus theta 0. And I'm going to assume the initial angular displacement was 0. Obviously, why would you not, right? We also know that the average, or excuse me, the initial angular velocity was 0 because it said it started at rest, so that was 0. So what we can do now is say theta is equal to 1 half. Now, the alpha we found was 69.81 radians per second, and then times 30 seconds squared, like that. So I'm going to get zero point 0.5 times 69.81 times 30 times 30, and this is going to give me 31,414.5. And that, based on these units that you see before you, is in radians, but we want it in revolutions. So I'm going to go ahead and write this over 1 to do a unit conversion. And I'm going to say pi radians oops, no, I want to say 2 pi radians. I'm going to say 2 pi radians is equal to 1 revolution, and therefore we can calculate that 31.414, which is really, really close to pi anyways. So I'm going to take that 31,414.5 and I'm going to divide it by parenthesis 2 times 3.14159, close parenthesis. And in this case, it gives me essentially 5,000 revolutions. Any questions on that? No questions? Now, as we said again, we could actually have calculated this theta using omega squared, or using omega squared equals omega zero squared plus 2 alpha parenthesis theta minus theta zero. That works as well. In fact, your book takes the time to do that, and you can actually work that out too. In this case, it gives you exactly the right answer, the same answer, in other words. Any questions? All right. So we got about 20 minutes left. I want to give you an idea about torque. So I've told you that torque is equal to force times lever arm, and I've told you actually a couple different ways. One of the things I said was torque is equal to R cross F. Now that is a new vector product. We learned the dot product in chapter. Actually, it might have been chapter. I can't remember if it was chapter nine. No, chapter eight. Might have been chapter seven or chapter eight, either one. I think it was chapter seven. We learned the dot product, but now what we have is a cross product. So I want to show you exactly what that is. Uh, to do a cross product, we can say the vector C is equal to A cross B. Okay. Now, there's a right hand rule associated with cross products. And basically, if you imagine the vectors A and B tail to tail, what you want to do is take your right hand, and what I tell my students to do is this pinky here along with this bone that goes through here. You can sort of picture that as like an axle. Even though it's obviously not like that, it goes down this way and then comes over here, and then there's all that. But you can sort of picture this as just one long bone that you can treat like an axle, and you want that axle parallel to the first vector. So in this case, I want A cross B. So A is the first vector. So if I draw what A and B look like, maybe I put A right here, and then I put B right here. And when they're tail to tail, I call that angle theta. Okay. But notice how they're pointing. I'm going to take this axle and lay it along A. So it's pointing along A just like that. Only now, since it's an axle, I'm free to rotate my hand through any angle I want, but I need to rotate it through an angle such that I can curl my fingers towards B. Again, my right hand is being used here. I can curl my fingers towards B through the small angle. Notice the theta is the small angle. If I went the other way, it would be all the way around. So I don't want that one. I want it to curl towards that. So that means when I stick my hand up like this to go parallel to A, then I need my hand to be like this so that I can curl down towards B. With that in mind, you see that my right thumb is actually pointing into the page, and in fact, that's exactly the direction of the vector A cross B. So the way I would draw this is I'd put a line right here, and then like that. And whenever you have a circle with an X in it, that's supposed to be you looking at the tail of the vector. So this is vector C, and it's pointing into the page. Because even though I drew this, and in principle the A and B could be in three dimensions, I'm saying, yeah, the A and B are in three dimensions, but A and B are both in the plane of my iPad. Therefore, this will be perpendicular. The big answer here is the C vector. The answer to A cross B is perpendicular to both A and B. And since A and B are both in the plane that is my page, then C has to be pointing into the page or it has to be pointing out of the page. And the right hand rule just told us that it points into the page. But let me show you how to go about calculating this cross product. So C equals A cross B. If I imagine A is equal to A sub X, I hat plus A sub Y, J hat plus A sub Z, K hat, and that B is defined similarly, then there's a quick and dirty way of calculating a cross product that we use, and it's by taking the determinant of a matrix. Okay, so you take the determinant of a matrix, and the first row of the matrix is just the I hat, the J hat, and the K hat. So I'm going to write up here I hat, and then I'm going to move over a little ways and write J hat, and then I'm going to move over a little ways and write K hat. So that's my first vector. That's my first row in this matrix. Now, the second row is the first vector. So I put A sub X, and then I put A sub Y, and then I put A sub Z. Now I take my B vector and I write B sub X, B sub Y, B sub Z. And now that's the matrix that I calculate the determinant of. Now we use the determinant that's a system of minors and sort of stuff like that. So what we do in physics usually, at least at this level, is we'll first expand upon that guy. So what we're going to do is we're going to say equals I hat. Now that I've actually covered or taken that I hat out, I've taken care of the first row and the first column because it turns out when you're doing a determinant, you're sort of making sure you hit every individual element in the matrix. So there's nine of these here. We want to make sure we hit all of them. But when you get a particular number, that number represents the number for each for the column it's in as well as for the row it's in. And then, well, actually, that's just very complicated. Let me just show you the formula. You calculate it and maybe make some sense of it. I'll show you another way to do it, and that might make more sense. But what I'm going to do right now is since I'm expanding upon the I, I'm going to cover up the first row and the first column because those are the rows and columns associated with I. And since I has it listed as the first row and the first column, there's a number I that represents the row number, and there's a number J that represents the column number, and those are 1, 1. So I would be called the determinant, let's say D 1, 1. And J hat would be D 1, 2, and K hat would be D 1, 3. So let me just put that in here so you make some sense of it. This one would be D row 1, column 3. The J hat would be D 1, 2. The AZ would be D, that's row 2, column 3. And the B would be D, and that is row 3, column 3. So this would be 3, 3. Similarly, I hat would be D 1, 1, and AX would be D, and in this case, it's row 2, column 1. So that'd be D 2, 1, so on and so forth. Now, when you expand upon a particular entry, like I did the I here, then you have to raise -1 to a power, and that power is I plus j. So that's 1 plus 1 because I hat was D11. Okay. Negative 1 to the 2 power is just positive 1. So what we do now is we take the remaining matrix, which is this, just this guy in here, and we do its determinant. And the determinant of a 2 by 2 matrix is diagonally down and to the right multiplied minus diagonally down and to the left multiplied. So in this case, I'm going to write A Y B Z minus A Z will be Y. So that's the I hat term. Now to expand upon the next one, I'm going to choose to do the J hat, and that means the first row and the second column will be eliminated. So I have now a matrix that's made up of AX, AZ, BX, BZ. In this case, I'm going to say plus J hat, and the negative 1 to the I plus J power. In this case, since J is the first row, second column, it'd be negative 1 to the 1 plus 2 because it's the first row, the second column. Now that's negative 1 to the 3, and that gives you a negative number. So the way I normally handle that is I just do my matrix backwards. So instead of going from top left to bottom right minus top right to bottom left, I go the opposite direction, and that takes care of that negative. But I'll just write it fully in the normal way here for this particular case, and you'll see what I mean. So now AXBZ minus AZBX. And now the final term, I got to expand upon K. So this will be K hat, and then that's negative 1 raised to the I plus J power. This is row 1, column 2. So, or excuse me, row 1, column 3. So this is negative 1 to the 1 plus 3, which is 4. Negative 1 to the 4 power is positive 1. And now you can see that I have as a matrix left AX, AY, BX, BY. So now I just do my normal 2 by 2 matrix determinant, which would be A X B Y minus A Y B X. Now, if I compute all this, what it's going to give me is A Y B Z minus A Z B Y I hat plus, notice the negative 1. I have to deal with that now, so I'm going to write it in the opposite order, and that's what I would have done by taking the determinant in opposite order. It's AZBX minus AXBZ, and then all of that times the J hat vector, and then plus, again, this one turns out to be positive, so it's AXBY minus AYBX, all of that to the K hat power. And that is the actual formula. And you'll notice that that's one of the things on our equation sheet, so you're welcome to use it. But really, I've never memorized that formula. It just made perfect sense how to calculate the determinant. So that's one way. That's the way your book teaches you. There is another way. I'm going to show you that real quick so you can make some sense of what's going on here. So another way you can do this is I can say C equals, I'm going to say I hat, J hat, K hat, AX, AY, AZ, BX, BY, BZ. The determinant of that. Now, what you can do is copy that first column. That's what I'm going to do here. I hat AX, BX, and then copy that second column. J hat AY, by. And now you can see that there's an actual really nice way of thinking about what the determinant is. Let me actually let me do this because this did not turn out as nice as I'd like it to be. I'm going to go in here and slip this little determinant word out of there. And what I'm going to do is lasso this thing. So I just pushed it a little bit to the right, hopefully. Uh, So how do we do it? Well, what I'm going to do is I need to make sure that I multiply every element of the matrix by every other element of the matrix in some sense. So what do I mean by that? I'm going to multiply these three guys. Notice that hits the I hat, which is row one, column one. It hits the AY, which is row two, column two. And it hits the BZ, which is row three, column three. Then I'm going to do the same thing with this one, which is row one, column two. AZ is row two, column three, and then BX, or excuse me, yeah, BX is row one, or excuse me, row three, column one. So you can see that in some sense we're doing each of them. And now I'm going to do this one as well this way. So what do I get when I do this? And this is just the first part. I have to do a subtraction next, which is the same thing, but in from top right to bottom left. So what I get is I hat times A, Y, B, Z plus J hat times A, Z, B, X plus K hat times AXBY. Now what I got to do is I've done the three top left to bottom right. Those are all my positives, which sort of looks like the determinant we were doing before. Now I'm going to go the opposite way to calculate the minuses. Okay. So in this case, I'm going to say minus I hat times, in this case, it's AZBY. And then the J hat, again, minus. And in this case, it's I hat. Ooh, that was supposed to be I hat AZBY. That works. Oops, I missed the K hat one. That's what I sorry about that. So I've got to do the K hat times AXBY. So let's do that. It'll be minus K hat. I even wrote it right, but I just started doing the next diagonal instead. So K times AY BX. And now I do I hat. So it's minus I hat. And this is AZ BY. And then I do minus J hat, which would be J hat times AX BZ. And I think you can see by combining like terms that you'll get exactly the same formula. So the I hat ends up giving me A, Y, B, Z minus A, Z, B, Y. And then the J hat gives me A, Z, B, X minus A, X, B, Z. And then the K hat gives me AX, BY minus AYBX. So again, exactly the same formula. Anybody have any questions on that? All right, we're gonna have to call it on that one. I might make some more videos and get y'all to watch them, but I think it'd probably do you better if I could actually uh, teach it to you in real time as opposed to just showing you the videos. So, and we're not far behind in terms of class hours left and that sort of thing. So I think that's just fine. You folks are free to go. Go ahead and chat me your first and last name. Don't forget to include that whether you're in the asynchronous class or not. But thank you everybody for coming, and I will see you all next time. Remember, you've got a online, or excuse me, a face-to-face test that is due, and I'm also opening the online test another night because one of our wonderful students forgot. So I'm going to open it up for both my NO2B and my 001B class. Darius, are you back online yet? Oop, don't know if Darius is there or not. Not yet. Uh, I'm sorry it's taken so long. I don't know what's going on, but it's all to be worked out. I know my dean has got involved as well as my dean's secretary, as well as the registrar and enrollment services. Go ahead, Jacob. You have a question?
Yes, about the face-to-face test coming up, is there going to be an online version of that? Like how for the last face-to-face test, there was a Zoom meeting that we could log into and do the test?
Yes, I will make one that requires you to use a camera, but also if your camera is attached to your monitor, then you'll need a mirror in addition to that. But as long as you stick to those rules, then you should be able to use it. So you'll need the lockdown browser, a webcam, and possibly a mirror. But if you have a webcam that's separate from your monitor, you can put the webcam off to this side or this side so that I can see from the top of your head all the way down to your writing surface as well as the computer monitor screen, the keyboard, and don't do any work below the surface. I want to see all that work that you're doing in real time. So as long as you keep that up, then yeah, that's a way you can do it at home without a proctor.
It's the same as normal then. Thank you.
Yep, you're welcome, Jacob. Anybody else?
Okay, I have something that's just but I'm so far behind still.
Mm-hmm.
It's chapter 6,
Mm-hmm.
specifically about the electron shell, something along those lines.
Okay, electron shell.
The gravity, yeah, I believe it's about the gravity of the electron shells. I
Okay.
might, it's the one with the extra notes on it, like the biggest block.
Is it from a homework problem or from a practice test or what? Or from an example in the textbook?
This test problem, I need to pull it up because it was in the online test, but I did not understand
Mm-hmm.
even a part of it. I ended up getting it on the first two attempt, getting those problems on the first two attempts. I'm just gonna pull it.
Okay.
I'm just gonna pull it. As well as yeah, I'm just gonna pull the question. The question's actually pretty short.
Oh, a
It's
spherical shell of inner radius R as a uniform density. Okay. Yeah, I know this problem. This is really a good problem. I love it. Let me draw it real quick to
I
give you
did
an
not
idea.
understand a single part of it.
Okay, so what has to happen for you to make any sense of this is you actually have to read the book kind of thoroughly because what they do when they cover gravity is they show you what Newton concluded, specifically that when you have spherically symmetric mass distribution, then only the matter that is closer to the center of the gravitational mass than you are, only that matter counts in calculating the force on you. So, for instance,
It's
if you're three-quarters of the way out from the center of the Earth to the edge of the Earth, then only the inner three-quarters of the radius of the Earth's mass contributes to the gravitational force you feel. So, go ahead. What were you saying?
wait, I thought is that related to his synthesized version of Kepler's third law?
No, but it's in that section anyways. Let's put it that way.
Because the only one I had to pull off from Little AI was apparently they called the nudes version of calculus third law, which is the period equals to 2 pi multiplied by the square root of the division between the squared radius
Mm-hmm.
times the gravitational constant. No, divided by the gravitational constant in the mass.
Gotcha. Yeah, that
It's
that sh doesn't seem to have anything to do with what we're talking about here. So
yeah.
let me show you what we're talking about in this particular problem. I'm
So
trying to get this centered up well, and I'm being OCD about
just
it,
like
so it's bad. It says a spherical shell of inner radius r and outer radius 3r has a uniform density rho. So what I'm going to draw here is r and an outer radius of 3r, and the density is rho, which is mass divided by volume. What is the magnitude of the gravitational acceleration a distance 4r from the center? So what we want to know is out at 4r, a equals question mark. Okay. So what we know is Newton's law of gravity says F is equal to G m1 m2 over r squared. And this object right here, I'm going to say has a mass m2, and this one is the mass of the planet, big M. But big M has to be equal to rho times the volume. So that means big M is equal to rho times, now the volume of this is the volume of a sphere minus the volume of a smaller sphere, and the volume of a sphere is 4 thirds pi r cubed. So I'm going to take 4 thirds, and now I'm going to take the 3r, which is the big radius, cubed, minus the r, which is the small radius, and I'm going to cube that as well. And that is the actual volume, is 4 thirds pi times basically 27r cubed minus 1r cubed, or 26r cubed. So this is rho times 4 thirds pi times 27r cubed minus r cubed. And that gives you, of course, 4 thirds pi rho times 26 times r cubed. Now, 3 goes into 21, so it doesn't go into 26, so we sort of just have to leave that. 4 times 20 is 80, 4 times 4 is 24, so that'd be 104 over 3 times pi rho r cubed. That's the total mass. Okay, so now I can say that the force on M2.
it just gave me the all it did was all the answers gave was what is it, a formula?
Mm-hmm.
That's not it. That's
We're not done yet, but yeah, this is the way you got to do it. Okay. So this is M2, and now we have to take the R, and that's actually the distance between the center of mass of the planet and the center of mass of the object, M2. So that distance is 4R, and that's in the bottom, but it's got to be squared. Okay. Now, what we say is F is equal to, this is F on M2, is equal to G times 104 over 3 times pi times rho times r cubed times M2, all that divided by 16 r squared. So now what we need ideally is 16 or something to go into 104. Checking 104 divided by 16. I think no, it only goes 6.5 times, but that's okay. We can represent the 16 by 4 times 4 and the 104 as 4 times 25. 4 quarters makes a dollar. So this would be 26 here. So this 4 cancels out with that 4 and leaves the 26, or excuse me, leaves the 26 at the top. And then this can give us also, I should point out that this cubed is going to cancel out with that and
Yeah.
just leave a 1 up there.
And then you cancel out a 2 out of 26.
And 4 times 3 is 12. So
So
I'm going to say 26 over 12. But yeah, like you said, I can reduce that by at least by
13.
2. And this would be rho. And then we have a R on top. And then we have a M2.
The 4
And
thirds part is the
this is 13 times 2, and this is 2 times 6. So the 2 will cancel out with this 2, and we get 13 over 6
you had
pi
to collect the
rho.
radius of the outer shell. You have to collect the velocity of the between the inner and outer shell.
Mm-mm. Okay, so that's the gravitational force at M2. Now we use Newton's second law, which says the summation of forces is equal to mass times acceleration. And this is all in one dimension, namely the radial dimension. So now I can say 13/6 pi rho r M2 is equal to M2 times A. So now you can see the M2's cancel out, and that should give us the A is equal to 13 over 6, oops, pi
Oh God.
rho
Oh,
r.
oh my God.
So that's the way
Yeah.
that's done.
Yeah, I did not understand what mattered the most in chapter 6. I thought it was the was it Kepler's law? No.
Kepler's law is important. I mean, that's one of the things you should learn, but you should also learn where that comes from. Kepler's
God.
first law is basically just the fact that uh, the only closed orbits that exist are conic sections, and specifically the ellipse is the general case, and that's what the first law says. The second law is conservation of angular momentum, and the third law is conservation of energy. But all of them can be found from Newton's laws. In fact, that was the first thing Newton did when he discovered this F being proportional to 1 over r squared. He immediately applied it to see if it gave him Kepler's laws, and it did. So.
Oh my God.
Any questions on that?
A slightly different one, but from chapter 5. It's the proportions of drag because because a lot of my problems that I ended up getting wrong of drag was not knowing the fact that sometimes drag is proportional to the square of the velocity.
Right. The two choices are the drag force is some constant times v,
It
or the drag
it
force is some constant times v squared.
oh, it's if it's if the object is in the not quite free fall moment,
Mm-hmm.
it's velocity squared. If it's falling through the air, it's velocity squared. The drag is proportional to velocity squared. This is mainly the conceptual stuff that I had problems with.
Mm-hmm.
If it's in the air, it's always proportional to the square of the velocity. If it's
I wouldn't say that generally. I don't know where you got that from, but in general, yes, there are situations where it acts more like proportional to v squared, and then there's other situation where it acts more like it's proportional to v. But pretty much you don't have the experience to know that. So yes, if the book tells you a specific thing like that, then that's something you want to commit to memory. But other than that, the problem needs to tell you which version you're using. But the key thing is you need to know how to figure out the terminal velocity.
Which is when the mass minus the drag force is zero.
Exactly. So you have acting on it a force mg, but you also have acting on it a force that is either b v squared or b v. So in the case of F drag 1, then you have b v is equal to mg,
Yeah, I think I got
means
it.
v terminal
Yeah, I think I got it on that one.
is equal to m over
It was just
b
a
times
proportion
g.
of v squared.
Hmm.
The integral for force is always one. Right.
No, the
Okay.
integral of f dot dl is work, but there's a lot of different ways you can integrate force. For instance,
Okay,
you could
because
take
I
the integral of force dt,
because
and
I
then you're talking
swore
about impulse.
because I swore there was a kinetic energy formula that because it's I think there were times where we used Hooke's law as k of x, k times x, not negative k times x.
I can't hear any of the words you're saying. You're coming in and out.
Yeah, so it's it's that in the Hooke's law. Where k is positive.
You went out again. Yeah, last I heard was Hooke's law.
Is is my mic actually working?
Not most of the time.
Uh, it was just trying to figure out Hooke's law with the what is it the between with the signage because sometimes it's not you because
Yeah,
sometimes
F
it's
equals
not
negative
negative.
kx. The negative is in there to tell you that the force acts in the opposite direction of the stretch. So if you're stretching it, it's going to try to pull it to make it shorter, and if you're compressing it, it's going to try to push it to make it longer. So
Oh
that's what the
yeah, there
negative's
we go.
for. But you can
I
drop
was
it
like
at any point.
I was like there was a difference between what is it stretching and compressing the spring.
Yeah. Hold on a second, though. You and I have been talking quite a bit. Let me ask
Yeah, I'm
Adriel
sorry.
or
I just
David or Beth. Anybody have another question? Like I said, I want to make sure I answer everybody's questions. They might not even be here. Sometimes they just log out and it leaves their name up there. But Adriel or David or Beth, do y'all have any questions? Feel free to type it in the chat if you can't answer. Nope. Okay. No problem, Adriel. Thank you, sir. All right. Well, go ahead, Adrian, then. I got a couple more minutes.
it's it's when do you use the positive? When do you use the signage for Hooke's law?
You really only
If
need the
it
sign to let you know which direction the force is acting. So
oh, okay, so it doesn't
I
matter if
never
it's
use the
compressed or
negative. Yeah, I never use the negative. I just
doesn't matter
always
if it's
use
compressed.
KX.
So it doesn't matter if it's stretched or compressed.
It does just in the sense that if you're stretching it, then the force points in the opposite direction that you're pulling it,
Yeah,
and
so the
if
signage
you're
matters.
compressing it, then it acts in the opposite direction than you're pushing it. But
Yeah, so the
that's the only
signage
reason.
matters.
Mhm.
It's just trying to remember if it's compressed, the resulting force is positive. The resulting force of the spring it
Well,
must be
that all
positive.
depends on how you set up your coordinates. But if you made your coordinate origin the equilibrium position and stretching it pushed in the positive x direction, then yes, the force would be
If
negative
if we're
when you
pushing
stretch it. and
If we're
positively
pushing
compress it.
the if we're pushing the spring in the negative direction, it should be positive.
Yes.
Okay. Uh, God. Oh God. So I'm still too far behind. I had to guess on some of the problems for the God. Uh,
Telling you, dude, you're going to kill yourself if you keep getting behind like this.
I
It's better
know
for
I
you to cut
can't
your losses and jump in to get, because if you're not keeping it up with the new stuff,
because I have
the
to
next
sit
test is
there
going to
and
kill you.
do. Yeah, I know. And then I just basically have to do chapter 8. Chapter 7, I just had to work out the last two.
Chapter 7 and 8 have a lot of material, but we've also covered 9 and a good fraction of 10 already. So,
Yeah,
you got to
yeah,
cut
it's
bait, dude.
not. Yeah, and I have to do chapter 8 because I haven't done anything on chapter 8
Hmm.
or chapter 9.
Yep.
And then you said after 10, 11, 12, 4, no,
11,
11,
14,
14, and
15.
15.
Yep.
Yeah, okay. Because I saw 36 and 44. No, 36 and 42 in the grade book. Why is that? Is it just there for any
Yeah,
reason?
so if we finish in time, then we'll jump to 36 is normally what we do. We do relativity, and then we do possibly elementary particle physics. Uh, I rarely get to those in the summer, though.
Okay. Oh God. Because because the integrals is what's gonna kill me more than anything else. Because
Hmm.
I thought if that was the case, then the integral force must be work.
Right.
Yeah. Okay. Yeah.
Okay, I just moved, and this is for the record on the video too. I just moved the homework for chapter 10 to 723.
I'm not gonna be able to get up to speed at all.
And the homework for chapters 9 to 716. So you have tomorrow as well to finish chapter 9. I'm not seeing chapter 10 conceptual. I got to find that real quick because it's not showing on here for some
The
reason.
homeworks matter, don't they?
Yes, they're very important for you to learn, but if you can
Been
still do
neglecting
well on the
it.
test, that can erase all the sins of your problems. So just keep that in mind.
Been neglecting it. But you could just
Yeah,
always come back to it just with reduced points.
yeah, and like I said, it's way more important that you do well on the face-to-face tests in the final. If I find towards the end of the semester, if I find that your test grades, especially your face-to-face and your online and your final exam grade are high, and your homework's bringing you down, I'm going to throw your homework out. I'm not even going to count it.
Okay. Okay. Can I also ask for the proctoring on Monday, the 21st?
Yes,
Okay. I'm not even sure if
but
I
you got to
got
be there
the
in the morning, or it's not going to work. So you need to be there at like 8.
oh God.
We might be able
Oh,
to do it in the afternoon, but currently it doesn't look like that's going to be the case. So just make sure you're prepared for that. And if you ask me again, like Sunday, then I'll be able to better tell you. But right now it's looking like we're only going to be able to, I'm only going to be able to proctor a test at from 8 to
uh,
10.
yeah, okay. Okay. Mhm. Got it. Thank you.
No problem. Well, have a good one, Adrian. David, Beth, anybody else? All right, I'm going to go ahead and say bye to you all. So thanks for coming and bye bye.